All right, so thanks very much for the introduction, Paul. It's indeed an honor and privilege to be able to speak here in this conference in honor of James Arthur. So I thank the organizers for their kind invitation. I guess the last time I was at the Fuse Institute. The mic is not. Yeah, is it okay? Is it better? Okay, so I was saying the last time I was in the Fuse Institute was probably 20 years ago when there was a conference here in honor of James' 60th birthday. So it's good to be back. Okay, so let me start. Okay. Okay. Good. Okay, so that's why I wanted to start. Yeah. So okay, now it seems to work. Okay. All right. So this is just a cue for me to say that I should tell some story. Okay. So a long time ago, in a galaxy far, far away, I was a PhD student. I mean, I was a postdoc just finishing my PhD, and during my PhD, I had studied data correspondence in the setting of exceptional groups. And of course, data correspondence is a means of constructing interesting representations and automorphic forms. However, so at that time, I was looking at a certain construction of certain so-called CAP representation, Caspital representations that look like isosceles series in the context of G2. So this is a work that Dihua alluded to yesterday as well. And I guess I was trying to struggling to understand what is the larger context in which these Caspital representations live. Right? So how are they surprising? Are they expected? Are they, what's their nature? So at this point, I think Gordon Savin, who was my mentor at that time, mentioned to me that you should take a look at Arthur's conjecture. So I didn't know anything about it. So I started looking at it, namely at these two papers. So I first started looking at this paper. This is from the 1989 Asterisk volume, where what we know as the Arthur's conjecture was stated in great detail. Okay. However, as a novice at that time, it was very hard for me to follow the what was written there because it was somehow too polished and too high level. Okay. But if you look at what was written, it says that our goal is to formulate some conjectures, and some of these conjectures were stated less generally in lectures at the University of Maryland. And so that led me to this other paper. I guess this is in lecture notes in mathematics, Springer lecture notes, proceedings of a conference in Maryland in 1983 on some problems suggested by the trace formula. And so yes, I think I'd like to pay tribute to this article because for me, this is the starting point of Arthur's conjecture. Let me briefly recall what was in this article. Okay, so in section 1, Arthur pointed out the following issue. At that time, Shellstead had shown that the tempered L packets of real groups satisfy, has a stable trace. You can add up the trace and it's stable. And so he was looking at what if you go beyond the tempered case, if you look at non-tempered L parameter, and he noted that now if you just add up the trace, they may no longer be stable. So he raised this question of how we can enlarge this to form a larger packet. And so for me, that is where the Arthur packet first appear. And but he doesn't advocate looking at arbitrary non-tempered L parameter. He said, let's look at those types that arise from what we now know as an Arthur parameter, right? So, and he raised the question specifically. So you start with Arthur parameter, you look at its associated L parameter, look at the L packet. Then he asked whether the representations in there are unitary. So these were some of the problems that he raised in the first section. Okay. Then in the second section, he moved to the global setting. So here he was interested in understanding non-tempered Caspital representations. So in the 70s, Kurokawa had, by numerical computations, produced examples of Ziegler modular forms, which seem to violate Ramanujan conjecture, or maybe he didn't know that they violate. But in other words, the Haeckel eigenvalues, do not take the expected absolute values. So so Arthur was trying to understand this phenomenon, and at that time there were very few examples. Okay, so one of the examples that he mentioned is called the Saito Kurokawa. So these are certain non-tempered Karp's forms on PGSP4 or SO5. Okay, and maybe in the same year, 1983, there was a paper by Petesky-Shapiro in Inventiones that sort of constructs this Saito Kurokawa hospital representations. How did PS did that? Well, he did it by using data leaf from metaplectic group, twofold cover of SL2. And so using this, Petesky-Shapiro was able to explain certain phenomena that were observed by people working on Saito Kurokawa representations. Okay, and so Arthur highlighted these familiar examples in this article, and in particular, he was trying to formulate a multiplicity formula for them. So at that time, I guess there were multiplicity formulas for example, SL2 coming from work of Labesse and Langlands. So I guess from there, it is natural to extrapolate, right, to the general tempered Karp's forms, let's say, what the multiplicity formula should be. But in these non-tempered examples, Arthur noticed that the naive extrapolation doesn't work, okay? Instead, you have to introduce a certain mysterious quadratic character of the global component group, okay? And so he mentioned that in this example, you have to have this, and in particular, a certain global root number plays a role in this multiplicity formula. Okay, he mentioned also one sentence that Petesky-Shapiro has checked that, for these Saito Kurokawa packets, the multiplicity formula involving this quadratic character is correct. Okay. However, when I look at Petesky-Shapiro's paper, I didn't see any verification of this. So probably it's some exercise that PS did and then just.
I was trying to spread out the blame in case that.
Ah, okay. I see. Okay. Yeah. But by the way, this paper of Petesky-Shapiro was beautifully written, and the Math SciNet review was also very nicely done. Provide a lot of perspective for me as a beginning, someone who just started a career. Yeah, in fact, the Math SciNet reviewer is in this room right now. So here's a trivia. And do you want to guess who reviewed PS paper on Saito Kurokawa lifting? It's not him. I wonder if the person remembers.
Somebody in the back.
Yeah, it's not me. I was only. So the reviewer is Marie-France Vinieras. So yeah. So thanks for the beautiful review, because it summarizes the context, highlight the main theorem. So for someone who needs a perspective and context, it was very helpful. Okay, so so since I couldn't find it in PS paper, I decided to do an exercise for myself to try to verify it. And of course, since the packets were constructed as data leaf from here, I have to understand the ingredient, right? I mean, if you don't understand the ingredient, you cannot understand the output. So that led me to understand, what do we know about Karp's form here? And of course, there was the famous paper of Wasperger. I guess there were two papers, one in 1980, but there was a later one, published maybe in 1990, but perhaps done earlier. Which actually, so what Wasperger did, which I will recall later on, was that he actually proved, I think in my opinion, the first instance of Arthur's conjecture. Okay, he actually described the discrete automorphic spectrum of MP2, and so the talk today is about extending this work of Wasperger to MP2N. Okay. Okay, so but before that, I'd like to recall, I would like to say what is Arthur's conjecture in just the context of classical groups. Okay, so I pointed out one this thing. This is a paragraph taken from the same page of this paper. So Arthur wrote that there are some conjectures, right, and they are stated in greater detail than is justified, for I have not had sufficient time to ponder them. However, they seem quite natural to me, and I will be surprised if they turned out to be badly off the mark. Okay, so for me, this is quite amazing because this is like 40 years ago, very early on, with very, very scant evidence, and he felt confident enough to say that, they must be right. Okay, essentially, yeah. So for me, it's amazing because even after, so firstly, history have shown that Arthur did have quite a lot of time to ponder these questions. In fact, for the next, it culminated in his book on endoscopic classification for symplectic orthogonal groups after 30 years. But I would say that even with hindsight now, for me personally, it's still surprising that they are so much on the map. So with that, I hope that that gives you some context about where this conjecture started. So for me, this paper in 1983 paper was a great paper to read. And if you haven't had a chance to read it, I suggest that recommend that you take a look because it was very early on. So everything is very raw somehow, very, the problems just really staring you in the face. Okay, so I guess to continue the tribute, I would like to recall what is the ultimate statement that come from this 30-year study. And I'll just focus on SO2n plus 1. So standard notations, F is a number field with ring of adeles A. Hn denotes the split odd orthogonal group, SO2n plus 1. So its Langlands dual group is sp2nc. And I'll let A sub n discrete be the space of discrete automorphic forms on Hn. So here then is the theorem, okay? Of course, the next few slides will elaborate on this theorem, for example, defining what various terms are. Okay, so the goal was to understand the space of discrete automorphic forms as a representation of the adelic points of Hn. So first statement says that there's a decomposition into submodules, A sub psi, okay, where psi runs over so-called elliptic global A parameters of SO2n plus 1. And moreover, this submodule is not irreducible. It's not necessarily irreducible, but it is a near equivalence class of representations, meaning that any two summands in there, at almost all places, their local component are isomorphic. So they are not exactly isomorphic, but they are nearly isomorphic. Okay, and of course, then after that, the next step, statement B, will sort of explicate what each of these submodules are. And the description is in terms of local and global A packets supplemented by a multiplicity formula. Okay, so let's, so as I said, the next few slides will explain various terms. So first one is elliptic A parameters. So in the context of SO2n plus 1, what are they? They are formal sum, finite formal sum of objects, pi I sort of tensor SDI. What are pi i's? Pi i's are cuspital representations of GL and I, and they are self-dual representations, so either orthogonal or symplectic type, depending on whether D is even or odd. So if D is even, I suppose the pi i's are orthogonal type, and the other way around. Okay, if Di is odd, and these symmetry conditions can be captured in terms of partial exterior square or symmetric square L function having a pole at s equals to 1. Yes.
Really stupid question. I thought that there were mass forms, cusp forms that came from unitary principles series.
Yes.
Previous slide.
Oh, previous slides.
So
yeah.
Do they have elliptic A parameters?
So for example, if your group were SO3, right, which is PGL2, then you see, then you will not be saying so much. I mean, so they will be the pi i's. So if the group is SO3, so I guess maybe I should run through this first. So what are the possible? So you're not saying too much in that case because your group is essentially GL2. Yeah, so we are just using Hospital representations of GL as parameters. Let's put it that way. So in that case, they are just themselves. So. Okay, so then the SDIs are, SD is the D-dimensional irreducible representation of SL2, and there's a numerical condition that the sum of NIDI has to be 2n. And finally, that the pairs are mutually distinct. Okay, so morally speaking, this psi, should be, I mean, it's a formal gadget like that. It's just a collection of data, right, with some conditions. But if you believe that Hospital representation of GLN give rise to n-dimensional representation of the, say, Galois group, okay, then you can interpret this direct sum as a 2n-dimensional, so that's where this numerical criteria, 2n-dimensional representation of the absolute Galois group of F cross SL2C, right? And moreover, is a multiplicity-free representation. That's what this last bullet point is saying. And moreover, the symmetry condition here is telling you that this representation a priori value in GL2n is actually valued in SP2nC, the dual group of SO2n plus 1. Okay, so for example, if you have a mass form on SO3, which is PGL2, right? Then, okay, so since we're doing n equals to 1, right? So you see there's not so many options. Either you take the 2-dimensional representation of SL2 and some character for pi, right? This character cannot be symplectic, right? So it has to be orthogonal type, so it has to be a quadratic character, right? Or else you just take psi equals to pi, a Hospital representation of GL2, right? So that will be like the mass form. So the mass form is just used as one of these parameters as index. Okay, you're not saying anything about it. Okay, so now, so as I mentioned, this guy is morally a Galois representation. But in fact, if you localize, so if you look at the place V, and you just take the local component at V, then then this psi V, let's say, is actually a Galois representation in the sense that because we have local Langlands correspondence for GLN, we can replace this pi I V by its L parameter. Okay, and then we can think of psi V, in this way, and it is actually now a 2n-dimensional symplectic representation of the local Langlands group with cross SL2. Okay, local Langlands group is, I think we saw it yesterday, is either the Wedelin group at a p-adic place or the Wey group at a real place. Okay, so that's elliptic A parameter. So you can see what the nature of the statement, the first statement is that there's a decomposition of the space of discrete automorphic forms into submodules, and this decomposition is indexed by a certain collection of Hospital representations of some GLs, okay, along with some integers DI, which you think of as representing a irreducible representation of SL2. Okay, now the next step is to describe this A psi, right, for each side. So so before that, just from this A parameter, we get some combinatorial data or group theoretic data. Okay, so firstly, for each V, we have a local component group, right? So we can look at the centralizer of this A parameter in the dual group SP2N and look at its component group. So if we think of the global parameter as a Galois representation, we write down the same statement, but since it is not, so we would define the global component group sort of by hand. In other words, for each summand I, we just introduce a basis vector EI for Z mod 2Z vector space. Okay, and that's the global component group, sort of by degree. And there's a natural diagonal map from the global component group to the product of the local one. So of course, all these local component group are finite, so this is a direct product. So this is a compact, a compact group. And what is the map? Well, so let's say you fix a V, you have to give a map from S psi to S psi V, right? So you have to tell me where the EIs are sent to there. So you think of EI as a linear map on the underlying vector space for the Galois representation, acting as minus identity on the ith summand and identity everywhere else. So on other summands. Okay, so this linear map certainly commutes with the action of psi V. Psi V. Okay, so it's an element in the centralizer. You take its image in a component group. That's what this map is. Okay, so and moreover, so Arthur defines a mysterious. So this adjective is taken from his 83 paper, quadratic character on the global component group. So I'm not going to repeat the definition here. It involves certain global root numbers in the adjoint representation. But just remark that if psi is generic, in other words, all the di's are 1, then in fact this character is trivial. Okay? And this will be the natural extension of the multiplicity formula of Lebesgue-Langlands in the SL2 case to the general static. However, as remarked, for example, in the Saito-Kurokawa case, this character is not trivial. Okay, and we'll see. Okay, so suppose now we have this global A parameter. It's supposed to give rise to a near equivalence class of representations. How is that? Well, to every Arthur parameter, we can say local Arthur parameter, we have an associated L parameter, right? So this is an L parameter of Arthur type. So what you do is instead of this SL2, right, this DI dimensional representation, you replace it by this block of characters of the Weil group. Okay, so at almost all places, of course, things are unramified. So you get an unramified representation of the SO2m plus 1 at V, and hence this determines a near equivalence class of representations. And the point is that whatever this A psi is, all the summands in there belong to this near equivalence class. Okay. Okay, so now this slide just describes this module. So for every place B, so if we fix psi, so what Arthur did was he defined a certain finite collection of representations, of unitary representations attached to psi V. Okay, so I guess there are various ways of describing this Arthur packet. Sometimes you hear people say that it is a multi-set of irreducible unitary representations equipped with a map to the irreducible representations of the component group. Right? So you say something like that. Okay, but yeah, so maybe just write down. So I mean, so somehow it is. I mean, you think of it as a correspondence, you know. So you can think of it as inside a character of the component group. But in this case, there is you sort of mod away the center across irreducible unitary representation of some subset. So of course, it has the two projections to the two sides. Okay, you can think of it this way. But so here I just repackage it. I think of it as a representation of the local component group together with the reductive group Hn, right? In this way. Okay, so one thing I want to point out was we are not looking at all irreducible representations of the component group, but those which are trivial when pulled back to the center of sp2n. Of course, at center of sp2n is just plus minus 1, right? Okay, so for those characters which are non-trivial on the center, they are supposed to index representations on the pure inner forms, Galois-Vogen. Okay. Okay. Moreover, one has this containment. You know, even though here we didn't explicate what this set is, but it is supposed to contain this L packet of attached to the L parameter associated with psi. Okay. So now, I have this local representation of this product group. I can take the restricted tensor product over all places, and now I get a representation of the this is the product of the local component groups and the adelic points of the group. Okay, and what is A psi? A psi is going to be a submodule of this restricted tensor product. Okay, so what it is right. So you have this, which is a representation of that. Okay. On the other hand, we saw earlier that there's a diagonal map from the global component group to this guy, right? So I can pull back by this map. So I think of this representation as a representation of this group. Okay, and then on the other hand, I have a character epsilon psi of the global component group, this mysterious quadratic character. So I can contract this pullback representation with that epsilon psi. I take the inner product over S psi, and what is left is just a representation of HA or HN of A, and that is what A psi is supposed to be. And is this last statement that people call Arthur multiplicity formula. Okay. Okay. So of course the statement itself is very condensed, right? And there to prove it, I guess there are many intermediate results one has to show. And one of them is actually this local Langlands correspondence. In particular, if you just look at generic psi v and look at the Arthur packets, then in fact they give a partition of the irreducible representations of HN FV. Also, just a remark that, of course, the proof is by the stable twisted trace formula as developed in the theory of endoscopy. And finally, just a remark that actually in a paper that appeared last year, Hiroshi Ishimoto, a former PhD student of Ichino, had established the generic part of the Arthur's conjecture for pure inner forms of SO2n plus 1. Okay, so he.
I'm sorry.
Yes.
In this, are there irreducible representations tempered, or it's all of them?
Yeah, so I think that you can put tempered, you can look at irreducible tempered, and then, yeah, that's right, yeah. Yeah, that's right, yeah. But of course, from there, one knows how to extend to all. Yes. Correct, that's right, that's right. Okay, so currently, for pure inner forms, SO2n plus 1, Ishimoto has established the generic part of Arthur's conjecture. In other words, he described this A psi for psi generic. Okay, and of course, one would like to complete the story, but it hasn't been done. So in particular, because he understood the generic part, he also obtained the local Langlands correspondence for these pure inner forms. Okay, so the purpose of this talk was about MP2N. Okay, so MP2N is a twofold cover of SP2N, both locally and globally, and we will consider the genuine automorphic discrete spectrum. So I always put a tilde, and this tilde means genuine. Okay, it means that we are looking at functions or representations that does not factor to SP2N. Okay, they really live on MP2N. And again, so the main problem is to understand this representation of MP2N adels, let's say, just as in the previous theorem for SO2n plus 1. Okay. As I mentioned before, the case n equals to 1 was done by Wasberger in the 80s using, and how did he do that? He used beta correspondence for MP2 cross SO3. So I'm going to review his results on the next couple of slides. Okay, so to formulate his results, so first, unlike earlier, now I have to fix an additive character, a non-trivial additive character of A mod F. Okay, and then the statement, the statement is going to look formally very similar to the endoscopic classification for SO2n plus 1. So first, it says that this space of genuine discrete automorphic forms decompose into a direct sum of submodules. Okay, and the indexing set is the same as for SO3. Okay, it runs over elliptic global A parameters. But one thing I wanted to note is that, unlike just now, I have a further subscript psi, which is this additive character. So this suggests that this decomposition depends on the choice of psi. Okay, and it does. Okay, so Wasberger in his papers focused on the case of generic psi. Why? Because as we said earlier, for SO3, the group is very small, right? You have the generic psi, and the only non-generic ones are just quadratic character tensor S2. Okay, and so the part of the spectrum that they correspond to are sort of well understood because they are supposed to be those Weil representations for MP2. Okay, so here take it that it is understood. So I just want to look at the orthogonal complement of those guys. Okay, and he showed that this orthogonal complement, this other part, can be described just using this generic global A parameters for SO3. Okay, so if we focus on generic psi, what it is just a Caspital representation of PGL2. That's it. Okay. So for each such psi, okay, so now I'm going to think of psi as just a Caspital representation of PGL2. Okay, let me look at a set of places where the local component is discrete series. Of course, this is a finite set because almost everywhere is unramified. So I can now compute the component group. The local component group is trivial unless the place V lies in this set, in which case it is Z mod 2. Okay, it's just from the local Langlands. If you're a discrete series, your L parameter is a two-dimensional irreducible representation. So its centralizer in SL2 is just the center, Z mod 2Z. Otherwise, it's connected, so you will not see any component group. Okay, so the diagonal map, so the global component group is just Z mod 2Z. There's only one Saman, right, in the global A parameter. So it's just this diagonal map from Z mod 2Z to a finite product of Z mod 2Zs. Okay, the number of copies equals the cardinality of this set. Okay, so then on this slide, we just formulate the result. So what Wasberger realized first was that under local data correspondence, so for a local field, the irreducible genuine representations of MP2N is in bijection with the union of the irreducible representations of SO3 and those are with pure inner forms. So pure inner forms of PGL2 is just a PD cross where D is a quaternion algebra. So given that, now he defines the A packet. Sorry, so let's say for a psi V, we are supposed to produce an A packet. Okay, so it is going to consist of one or two representations. Namely, you take the so because you have this statement in front, right? So you take psi V. Psi V is a representation of H1K. So you can use this to produce a genuine representation of MP2N by this theta leaf. Okay, call this guy pi V tilde plus. And then on the other hand, you can consider Jacquet-Langlands transfer of psi V to the inner form, to the quaternion algebra. And then you produce another representation here by theta psi. Okay. Now, of course, if psi V were not a discrete series, the Jacquet-Langlands transfer will be 0. And then you won't have this second representation. Okay. So you produce a set with of size 1 or 2. Okay. So instead of thinking it as a set, you can use this the way I wrote it in the earlier slide, where I think of it as a representation of in this sort of way. Yeah. So okay, and then all right. So now if you just pick one of these signs, right, at every place, you can produce a global representation. So the epsilon V plus or minus, either plus or minus, right? And then what is the multiplicity inside this piece? Well, it's 1 or 0, okay? And so that is the multiplicity formula, okay? But when is it 1? It is 1 when the product of the signs, epsilon V, is the global root number of psi, of the Caspital representation psi. So this is in contrast to SO3 and its inner form, where you would put the product, the multiplicity is 1 if the product of the sign is 1. Okay, as I said, this epsilon psi is 1 for generic parameters. But in the MP2 case, you see that it is not. It is some arithmetically interesting number. Let's put it that way. Okay, okay, so that is Wasberger's result. As I mentioned, for the Saito Kurokawa representation, this was one of the main motivating examples for Arthur to introduce this epsilon psi. Right? He noticed that in this case, you cannot just take trivial character. But what is the source of that? Since these things are produced by theta leaf from here, the source comes from here, and it actually is from this multiplicity formula on MP2. Okay, so given Wasserger's result, so you just believe it, then you can try to extend it to MP2N, okay, and somehow as a natural extension, and that's the theorem. So theorem is that for general N, you have this decomposition into submodules indexed by elliptic global A parameters of Hn. For every V, you have a local A packet, and the multiplicity formula looks the same way, except that this epsilon tilde psi is a character which is modified from Arthur's character, epsilon psi. So there's a certain, you may call metaplectic modification, eta tilde psi, okay? So what is that? Well, okay, so this is a character of the global component group. So I just have to tell you, what value it takes on each of these basis vector EI, right? So the question is, do I introduce an additional sign or not? And the answer is, well, if the pi I is orthogonal, you don't. If it is symplectic, you look at this. Okay? So when n equals to 1, this reduces to Wasserger's multiplicity formula. Okay, so that's the theorem for MP2N. Okay, so I tell you the theorem now. I will just the rest of the time I'll be discussing how one arrives at this final conclusion. Okay. All right. So it seems that there are two approaches that one can think of to try to prove this theorem. Okay. So one is, well, since Wasserger used the data correspondence for MP2 and SO3, maybe we should just look at the data correspondence for MP2N cross SO2N plus 1. That seems natural, right? You work for n equals to 1, why not try to push it to general N? So that's one route one could take. The other approach was, after all, what is the theorem saying? The theorem is comparing the discrete spectra of MP2N with that of SO2N plus 1. Okay, so whenever you have such comparison, of course, the trace formula has to come to mind as one of the tools to try to effect such a comparison, right? Well, the problem is that in order to have such a trace formula comparison, it would seem that one would have to develop a theory of endoscopy and stable trace formula for this nonlinear covering group, MP2N. Okay. And in fact, both approaches were being developed and pursued independently, maybe from 15 or 20 years ago. Okay, there were people trying to pursue each of these. But we'll see ultimately that actually the theorem on the previous slide is ultimately proved by combining these two approaches. Okay, so I'm going to describe work that was done for each of those approaches, and then finally what happened at the end. Okay, so let's start with the data correspondence one. Okay, so let's assume K is a local field different from C, fix a non-trivial additive character of K. Then there's this theorem, local theorem, that extends what Wasserger did to classify the irreducible genuine representations of MP2N. Okay, says that under data correspondence, data psi, you get a bijection between the left-hand side and the right-hand side is a disjoint union of irreducible representations of SOVN, as Vn runs over all 2n plus 1 dimensional quadratic space of discriminant 1. So these are all pure inner forms. Okay. Of course, in the p-adic case, there are only two terms in this union. There's the split group and the non-split one. That's it. Okay, but in the Archimedean case, there are more because there are these signatures. Okay. Okay, so this was proved in the over the rails by Adams and Babesh in 1997, and Gordon Sabin and I did the p-adic case in 2012. Okay, as a corollary of this, what happens is that you get a local Langlands correspondence for MP2N, okay, because you have the local Langlands correspondence for pure inner forms of SO2N plus 1, say by the work of Arthur and also Ishimoto. And Moglen herself independently did that as well. So you can combine this bijection with the local Langlands for SO2N plus 1 to get a local Langlands for MP2N. Okay. The point now is that somehow there are more representations here because you have to take all the Vogan packets. So in particular, you're sort of using all characters of S side. So you don't mod away center or things like that. Okay. Okay, so that's the local theorem that extends quite naturally what Wasperger did in the case n equals to 1. Okay, and the global case, by using global data correspondence, Ichino and I proved in 2018 the following theorem. So first we proved that there is a decomposition like that, okay, where psi runs over global A parameters, and moreover, each of these pieces are, sort of form a near equivalence class, okay? And moreover, when psi is generic, we have the local A packets. Why? Because they are just given by the LLC for MP2N on the previous slide. Okay, because the psi is generic, so the A packet should be just the L packet, right? So we just take the L packets as provided by the previous slide, and then we verify the multiplicity formula holds for this generic part of the automorphic discrete spectrum. Okay, so if you look at this theorem, you already come very close, right? The only thing that remains are just what about those non-generic A parameter psi? Okay, so but we didn't say anything about them in this theorem. Okay, so not surprisingly, the proof of this theorem requires knowing the automorphic discrete spectra of SO2m plus 1 for all n. Okay, and due to Arthur and Ishimoto. So we need to know it for split SO2n plus 1, we need to know the complete result of Arthur. But for the inner forms, we also need to know something on the inner forms, but just for the generic part, and that was supplied by Ishimoto. Of course, his work was supplied after our paper appeared. I mean, we take it as a hypothesis in our paper, and then Ichino give it as a thesis problem to his student. Okay, now, so I mentioned this is by global data correspondence, so it might give one the impression that one is extending what Wasperger did, which is to consider the data correspondence for MP2N cross SO2N plus 1. But this is not the case, because what we actually did was to use the global data correspondence for our fixed MP2N together with a very large split special orthogonal group. Okay, where R is very big, let's put it that way. Okay. And another key input is the beautiful result of Jianshu Li, and I will recall what his result says. Okay. So his result is formulated in the following way. So suppose you have an abstract representation of MP2N adels. Okay. So this is not automorphic, just abstract. Okay. Now you can consider it's the local data leaf of each local component. Now, because you take R to be very big, we are in the so-called stable range. So all these local data leaf are not zero. Okay, so you have a non-zero irreducible representation. You tensor them together, you get some abstract data leaf of pi tilde. Okay, on this large special orthogonal group. Okay, so Jianshu Li's theorem says the following. He says that, well, let's look at L2, the genuine L2 of MP2N. So the square bracket is standard notation for the automorphic quotient, GA mod GF, okay? Now, that's a unitary representation of Hilbert space, okay? And maybe we are trying to understand its decomposition, but whatever it is, it has some decomposition as a direct integral of irreducible representations with some multiplicities, okay? Whatever this is, okay? His theorem says that now, if you insert this data abstract, okay, you write out this integral, okay? Now, this is now a direct integral of irreducible representations of these groups. Okay, I should say that the other thing that also shown by Jianshu Li was in the stable range, if you start with a unitary representation, pi tilde v, its data leaf is also unitary. Okay, that was what Jianshu did in his thesis. So, so these guys are actually unitary representations. We can form the direct integral using the same measure and whatever this measure space is that you're integrating over. Okay, now his result says that this abstract unitary representation is contained in the automorphic L2 of this large orthogonal group. Okay, so what is the consequence of this? So for example, if you have a, yeah, so maybe this, okay, so the consequence is that if you, suppose you have a pi tilde that occurs discretely inside this L2. Let's say it occurred 3 times, the multiplicity is 3, okay? Then here you're going to see 3 times of its abstract data leaf occurring here, also discretely, okay? So this shows that the discrete multiplicity of theta pi tilde is at least as large as the discrete multiplicity of pi, okay? So for example, suppose you take a, now you just look at the discrete spectrum, which is the thing. Yes. Yes, that's right. Yeah. So it's important that R is bigger than N here. Yeah. So you have to go sufficiently large, then it preserves unitarity. Okay, so yes, that's right. Yeah. So you can pick your R, doesn't matter. Yeah, which one. So okay, so for example, right, suppose you look at the discrete spectrum and you look at a near equivalence class occurring in the discrete spectrum. Okay, that's kind of like our A tilde side, right? And it shows that this near equivalence class is kind of faithfully replicated in this over here. Okay. Okay. Now, so we have that result in general, and that actually, yeah. So maybe let's go back a bit. So that result allows us to have this decomposition. So because you see, for example, if you take any, as I mentioned, you take any near equivalence class in the discrete spectrum, this result shows that when you apply data leaf, abstract data leaf to the representations in there, right, it continues to occur discretely inside here. Okay. Now, but you have Arthur's theorem for this guy. So which means that those collection of nearly equivalent representations belong to some global parameter. Okay. And so now you have a global parameter on this large orthogonal group. Okay, you need to trim it down to make it the right size, right? And that's what we'll say next. Okay, so if psi is generic, okay, then see in the previous corollary we have an inequality like that. But a key proposition for generic psi is that when psi is generic, we have equality. Okay, this shows that, for example, if we start with a certain near equivalence class here, it is just obtained by pulling back. Okay, as I said, after you do the data leaf, you have an Arthur parameter. We have to show that the Arthur parameter is of the form psi plus S to R. Okay, so this is maybe in the spirit of Adam's conjecture for data leaf, right? Because of that, you can now just remove this summand. Then psi will be a 2n dimensional summand, and you define that to be the A parameter for the given near equivalence class that you're considering. Okay, so the upshot is that the structure of this A tilde is the same as the data leaf is kind of one-to-one thing, so it preserves the whole structure. And so, for example, you can transport the Arthur multiplicity formula for this large parameter on SO2n plus 2r plus 1 to psi. Okay, now, for this large group, it's a non-tempered parameter, I mean non-generic parameter, right? So because of this S to R. So you have this quadratic character, okay? When you restrict that to the component group for S psi, so the component group for this is just component group of S psi cross an extra copy of Z mod 2Z coming from this summand. You can restrict that character to this subgroup S psi, and it is precisely this epsilon tilde psi. Okay, so that's how we get this epsilon tilde psi. Okay, so just a remark that if we know the equality holds for all psi, not just generic one, then we would have proved the full theorem in the same style. Okay. Unfortunately, we don't. All we did was that we check it for MP4 by hand, because MP4 there are only a few families of non-generic A parameters, so you do it by hand, and then. Okay, so another remark is that two of my students, Ray Chen and Jialiang Zhou, use this same idea to establish the generic part of the Arthur's conjecture for pure unit forms of O2n and Un. Okay, so that's the story for data correspondence. It come almost to the end, except it missed this the non-tempered A packets. So now let me change to the other track, which is endoscopy and trace formula. Okay, so in the 1990s already, Jeff Adams and subsequently David Renard had developed a theory of endoscopy for MP2NR. Okay, in this theory, the endoscopic groups are MP2A cross MP2B, where A plus, so AB is an ordered pair whose sum is N. Okay, but in his PhD thesis from 2011, Wenwei Li developed a variant of this theory, where now the endoscopic groups are SO2A plus 1 cross SO2B plus 1. Again, AB is an ordered pair whose sum is N. Okay, so more precisely, what does it mean to develop a theory of endoscopy? Okay, so for every ordered pair AB, as such, he defined transfer factors. Okay. Then he showed the existence of transfer, like comparing stable orbital integrals on HAB with invariant orbital integrals on MP2N. Okay. He also proved the ordinary and weighted fundamental lemmas. Okay, so he did everything basically. Okay. So that's what I mean by developing a theory of endoscopy. Of course, he also relates his theory with the one developed by Adams and Renard. Okay, they are compatible in some way. Okay, now starting from his thesis work, Wenwei also developed the theory of invariant trace formula for general covering groups. In fact, he brings it all the way to probably 1992 or something, where Arthur established the full invariant trace formula for linear group, reductive groups. Okay. So at this point, since you have the invariant trace formula and you have the theory of endoscopy for MP2N, you are in a position to consider the stabilization of the trace formula. Okay? And this he finally did over 2 papers. First paper in 2015, he stabilized the elliptic part of the trace formula for MP2N. And in a tour de force in 2021, he established it fully. Okay. Yeah, first paper was 150 pages, second paper was 350 pages, something like that. So I have not seen any stabilization or any trace formula that cannot be considered a tour de force. Okay, it's just the way it is. Yes.
In this formula, I suppose you have to define the discrete part of the trace formula, right?
Oh yeah. So I think yes. So maybe I omitted discrete here. Yeah. So yeah, that's right. Yeah. So I should put discrete as a subscript. Yes. Yeah. Okay, so now that you have this, you might imagine that you should be able to prove Arthur's conjecture for MP2N, right? Since you know it for HAB. Right? That's what Wenwei subsequently tried to do. But before I come to that, I want to say that even just using the weaker result from 2015, just the elliptic part, the stable elliptic part, you can already have some application. So firstly, just knowing the elliptic part, you should be able to define tempered L packets for MP2N already by global, local sort of things. And then, you would have 2 definitions of L packets, one from data correspondence and one from this trace formula approach. And you may ask whether they are the same or not. Because another way of asking the same question is to say that if you look at the packets defined by the data correspondence, do they satisfy these endoscopic character identities or endoscopic character relations, ECR, I guess. Okay. And the other question you may ask is, do they satisfy this local intertwining relation, which plays a key role in the application of the trace formula? Okay. You'll hear more about this in Tasho's talk later, I'm sure. Yeah. So, and both, both these parts have been established. So for the ECR, it was done by one of my PhD students, Chai-Hua Luo, and Ishimoto did the LIR. Okay, so here I just flesh out the results. So what is endoscopic character identity look like? It kind of looks like what you expect. Okay, so if okay, so I see that I have not violated the principle of having typos. Okay, so this would be a psi. Okay, so it just you look at a parameter, right, and it defines 2 packets, one on HAB and one on MP2N. You look at the stable trace, stable character for the HAB character. You pull it back by this transfer map, And you're going to get some linear combination of characters in pi tilde. The coefficients, so what is the S? The S is this element here. Okay. And notice that there's this epsilon factor playing a role. And this is where finally, from the trace formula viewpoint, right, this is where in the multiplicity formula, you see this root number. Okay, so last slide. So finally, in a preprint release just last year, Wen-Wei completed the story. So in particular, he constructed the non-generic local A packets and he verified the expected multiplicity formula. Yeah. So so in that sense, the theorem is finally proven. Okay. Now, however, I said earlier that this theorem was finally used by combining these two approaches. The reason is because his work is not independent of the data correspondence results. Okay. Ideally, right, one would like to say just use the trace formula and prove the theorem. Yeah, but I think people believe that still can be done. It's just that it may take longer, right? So, but since you have the results of data correspondence already, it allows you to short circuit certain steps. Okay. And so in particular, his work used as input my results with Ichino in the form of this no embedded Hacker eigenvalues property, and also use this tempered ECR of Chai-Hua law. Okay? And the purpose is to, why he used this was to construct the co-tempered local A packets and verify their ECRs. Okay, again, you will hear more about this in Tashio's talk later, not in the context of MP2N, but okay, so in the end, as a summary, the result was obtained by a combination of data correspondence and stable trace formula. But if you're a purist on either side, feel free to continue to use your favorite methods to prove the theorems. Okay, so with that, I thank you and all the best to Jim.